to this tutorial. And now I go to share the file. Okay, here we have for the set 2 the following exercise. That's what we have here. We have the coordinate system, x, y, and we have a rod here with a particle, in our case here, mass m, with constant angular velocity omega, which is in the direction of z here. And this rod rotates about the coordinate origin here, and mass m moves on the rod with constant velocity vr. That it means that you have your mass moves along this rod here and describing such path. That it means we have here the position r, the vector position r, and we have here, instead to use the coordinate system x, y, we use the polar coordinate system, what we saw it in the slide on part 1. Yeah, what the last week. Yeah, you can see the slide as well as the video. And in this case, we have here given the velocity Vr along AR direction and omega, which is V dot, and this is along Z direction. And we take the initial conditions here at time t equal to 0, the mass is at this position here at the origin, r is equal to 0, and the angle phi is also equal to 0. What it's asked for is to determine the equation of the displacement curve r as function of phi. Determine the velocity v as function of phi and the acceleration a vector as function of phi in polar coordinate, as well as their magnitude v and a. That it means we have to look for the vector of the velocity as well as for the acceleration and their magnitude, and determine the component of E tangential and the normal one of the acceleration vector. Now, if I return back now to get I said that it's the part 1. I put the video on YouTube, and already I sent the link on Moodle. Please look to the video as it was proposed by student. Look to the video, you will find the part of this lecture of the second part, let's say, of the first lecture. Yeah, that is mean the not the part two. Part two it started today, and the part one, as I have done only the first lecture. The last week we had technical problems. I had technical problems, and I put the video of the lecture on YouTube. If someone has not the link or he didn't got the link to this video, please let me know per email. Okay. Now, one moment, I have to take my tablet. That can I write easily? And now starting. What we have, we have, which is given for R, which is equal to R dot, and this is given as constant. And we have also omega, the angular velocity, which is equal to phi, phi dot, and this is also its constant. These are here given. Now, if I look to, by definition, we know that R dot is given by dr over dt. This is the position. Then we have here the position, and the time derivative of the position gives only the velocity. Then if we make now by for what is asked for R as function of phi, then what we can use what we call the chain rule. Then we have R dot, which is dr over dt, and this is equal to dr over diff phi multiplied by d phi over dt. That it means here we have, by definition, velocity is the time derivative of the position. As the position is depending on the phi, the angle, in this case, we can make that dr over dphi multiplied by dphi over dt. When you have dphi here, dphi here, each term cancel each other and we become to the r over dt. That is means we have here, this is, we can write it by dr over d phi multiplied by phi dot. That it means, if we look well, this terms here, it's only phi dot. And this is can be also written by dr over d phi multiplied by omega. As we know that omega, it's only phi dot. This is here what we called the angular velocity, yeah, which is in our case along z direction. That's what we have here. We see that r dot for r, the velocity along the radial direction, it's only here r dot, and we can write that vr, it's only dr over dphi multiplied by omega. Then what we do is only to separate the variable. That's what we have here. We write separation of variable. Then what we have here, dr, we can write that dr, it's only vr divided by omega multiplied by dphi. Why we write this? This is correspond to the position, the first term, the left hand side, and the right hand side correspond to the velocity which depend on phi. Now, if we make the integration that we have here, integration with respect to each variable, then what we have here, we have the integral of dr, it's equal to vr divided by omega integral of dphi. Why we write this term or this ratio Vr divided by omega? Because we said that in the exercise that Vr and omega are constant. That it means they don't depend on phi, the variable phi. They are always constant at each angle. In this case, we can put this term here out of the integral. Then what we get in this case, if we integrate, we have r, which is equal to Vr divided by omega multiplied by phi plus constant of integration C1. We have from initial condition R is given on the exercise by phi equal to 0 is equal to 0. Then it means that in this case, what we have here C1. If we use this equation here by phi equal to 0, we have R equal to 0. Then we get C1, which is equal to 0. Then we can get the following equation that here, then here we can say that R vector as function of phi is equal to R as magnitude in radial direction ER, and this is equal to VR divided by omega multiplied by phi in AR direction. This is what is asked in the first part. Now coming to the second part, which is asked for the velocity v as function of phi. What we have by definition, we have the velocity v, it's only the time derivative of r, the pixel position. But this means that it's the r over dt. Now, if we look to the vector r, we have here r phi, it's only Vr divided by omega multiplied by phi in with the basis vector AR. Now, if we look to this, what we have here equal, if we replace R by its expression given in the first question, now we have here d over dt of the expression of Vr divided by omega multiplied by phi AR. In our case, we have VR is constant and omega as well is constant. That means they are time independent. Then in this case, we have here, we can write that this term, the term of the time derivative, then we have here three, let's say, terms. They have this ratio here, VR divided by omega. We have phi, which also depend on time. If we integrated that d phi over dt, it's only phi dot. And we have also ER. And ER is changing also with the time. Then in this case, what we have d over dt of VR over omega. This multiplied by phi ER plus we have VR over omega multiplied by phi dot ER plus VR over omega multiplied by phi multiplied by ER dot. Then as we said, we have three terms here, the product of three terms. We have, when we make the time derivative, we take the first part here. As VR is constant, omega is constant. In this case, here, this is equal to 0 because it's time independent. Yeah. Then we have the second term where we derive with respect of we derive phi with respect to the time. The third term we derive ER with respect to time t. We know from the lecture that this term here ER it's only phi dot multiplied by phi. You look to the slides, as I said, you have E dot R as is changing with the time. It's this either the rigid body or the particle. It's moving. As it's moving, that it means it moves. If it moves, then it means it's time dependent. It's changing. Yeah, the coordinate system is changing with the time. And we have, for example, E phi. If we have E phi dot, it's only minus phi dot ER. Now, if we're on place, then we get here the following expression that V it's given by VR divided by omega multiplied by omega multiplied by ER. Why? This is phi dot, I make it in another color. We have phi dot it's only omega. Yeah. Then in this case, that's replaced by omega, and we have the second term plus plus here VR over omega, we have phi and multiplied by phi dot E phi. Then we have here phi dot E phi and this one, it's only omega. Then it means we can write this equal to VR divided by omega. We can see that we write it simple, yeah. Um, then we have here equal this term here, omega go with omega, and we have this term phi dot go with omega. Sorry, it's not VR, as I said, it's here we have VR, and here omega goes with omega, yeah? Or phi dot goes with omega. Then it means we can write now that it's only VR multiplied by ER plus VR phi E phi. This is, now we can write it in vectorial representation. Then we have two components here. V has two components, one in radial direction and the second one in circumferential direction. Then we can write that V has the component as vector like this, has VR in radial direction, and we has VR in multiplied by phi in circumferential direction. This is what it's asked for the second part. Now it's asked to get the magnitude of V. V here we can write it also as absolute value of V vector. In this case, what we have VR square root square plus VR phi square. This is the magnitude. Then it means we get here V by VR square root of 1 plus phi square. Now we have the vector of the velocity as function of phi, and we have its magnitude. Now, coming to the second part of the second question, we have to consider the acceleration. Now we have to consider the acceleration. Then in this case, what we have by definition, A, and I write it here, acceleration A, and also its magnitude A. That's what it's asked for. Then we have the acceleration. It's by definition, it's only V dot. That is the time derivative of the velocity vector and now if we look to the expression of V here has a radial component and circular or circumferential component, then we replace it. That it means what we have here, we have d over dt of the velocity, and we have VR plus VR multiplied by phi F. Now, if we look here, the time derivative is the same principle as before. We have the first part here. When we make the time derivation, we have to consider the fact that to make d over dt of VR plus multiplied by AR plus d over dt of ER multiplied by VR. The same principle here, that we have d over dt VR multiplied by phi EV, then d over dt of phi, d over dt of phi multiplied by VR EV, and d over dt of EV multiplied by VR phi. Then we have in total 5 terms, let's say. Then we have in this case here, I write it here, A. Then we have V dot, this is equal, V dot, the first part, R, ER, plus VR multiplied by ER dot plus V dot R phi if E plus VR V dot if E plus VR phi E dot phi. Then if we can simplify it or to explain it, that it means this term here by time derivative get coming, we get these three terms here. And we have the second one, the first one, this one gives this part here. If we make the time derivative, as I said, of the first terms, we get the two terms here, first and second term. And if we make the time derivative of the second part here, then we get third, fourth, and fifth terms. Now what we know? We know that VR is constant. That it means here this terms is equal to 0. And here also it's equal to 0. Now we have phi dot, we have ER dot, and we have E dot phi. What we know, I make it that with here in color that ER dot, it's only phi dot phi. And we have I don't know why it's not writing. And we have one moment, please, yeah. You can wait, please, one moment. Yeah, I have to check why the pencil is not working on the display. Okay, I returned back. I think it's so, the screen is so sensible. Yes, we had, as I said, that ER dot, it's only phi dot E file and E file dot, it's only minus of phi dot ER. This is what we have by um, demonstrated it, where we demonstrated it during the lecture. You look to the slides. And now if I come to this part, what we have here, we have this term which is equal to 0. We have this term is equal to 0. And we replace ER dot and if dot by this expression here. Then it means if we do so, that we get here A as vector of VR multiplied by phi dot A phi plus VR phi dot A phi plus VR phi multiplied by minus phi dot AR. Now, if we look here, we have it returned back this the problem. Okay, I will close it and I will return back. It seems that doesn't work. Still, this problem here. I return back, yeah. Be patient with me. It seems still that the pencil is not writing. I will close it completely.